Ever just stop and look at a massive steel bridge spanning a river, or maybe the wing of a commercial airliner, and wonder what exactly keeps that from just ripping apart under all that immense pressure? I mean, we rarely think about the invisible physical rules holding our built environment together, but engineers, they obsess over them. So in today's Explainer, we're diving deep into the hidden physics of shear stress and structural joints. We're going to see exactly how materials behave when they are pushed to their absolute limits, and how we use that knowledge to literally build the modern world. Okay, let's take a quick look at our roadmap for today. We'll be covering 1. The basics of shear stress, 2. Complementary shear and strain, 3. Storing strain energy, 4. We'll apply this to riveted joints, and 5. Designing against failure. Trust me, the theoretical physics we start with is going to perfectly connect to some really cool real-world engineering. All right, section 1, the basics of shear stress. What actually happens when forces start sliding against one another? Think about a thick deck of playing cards for a second. If you push the top half to the right and the bottom half to the left, what happens? They slide, right? Well, that sliding action is essentially shear stress. Technically speaking, it's the tendency for one part of a solid body to slide over or shear from another part. This happens when it's subjected to two equal, opposite, parallel forces that aren't perfectly aligned. They offset, and they basically try to slice right through the material. As you can see here, those two parallel forces, labeled P, are pulling in opposite directions. And notice that dotted line right down the middle, section L to M? Those forces are desperately attempting to slice that rectangular block perfectly in half along that line. Now, engineers calculate this average shear stress, which is represented by the Greek letter tau, using a super straightforward equation. Tau equals P divided by A. That's just the sliding force divided by the area of that cross-section. So, obviously, the larger the force, or the smaller the area resisting it, the higher your shear stress is going to be. Moving right along to section 2, complementary shear and strain. Let's see how nature demands balance. This beautifully illustrates how materials actually maintain that balance. Imagine that small rectangular element, A, B, C, D, is stuck inside a massive piece of steel. If we apply our initial shear stress, tau, along the top edge AB and the bottom edge CD, what happens? Well, those forces create a turning moment. It's a couple that basically wants to spin that rectangle like a steering wheel. But, buildings aren't just spinning around. They're in equilibrium. So to prevent that rotation, the material itself instantly induces an equal and opposite force on the vertical planes, AD and BC. We call this tau prime, or the complementary shear stress. It's a fundamental rule. Every single time you have shear stress in one direction, you are guaranteed an equal complementary shear stress at exactly 90 degrees just to keep the whole thing from spinning out of control. Now here's an absolutely crucial point. We have to distinguish between the invisible force applying the pressure and the physical distortion that actually results from it. Stress is the cause, that's your sliding force. Strain is the effect. When you apply that stress, the previously perfect right angles of our square block physically warp into a parallelogram. That angular distortion, that tiny change in the corner's angle that engineers measure in radians, that is your shear strain. So engineers need to know exactly how much a specific material is going to warp when a certain amount of stress is applied to it. As long as we're within elastic limits, which basically just means the material will snap back to its original shape when you let go, the shear strain is directly proportional to the shear stress. And this ratio? It's called the modulus of rigidity. It's essentially a mathematical constant, almost like a structural fingerprint, that tells you exactly how stiff a material is. So steel has a really high modulus of rigidity, while something like, say, jelly has a very low one. Let's jump into section 3, storing strain energy. Because there's actually energy hiding inside these materials. Think about stretching a rubber band. You're doing mechanical work, right? And that work doesn't just vanish. It gets stored inside the rubber band as potential energy. Well, solid metals do the exact same thing when they're subjected to shear stress. This elegant little equation shows us strain energy, represented by U. It reveals that the energy stored is equal to the shear stress squared, divided by twice the modulus of rigidity, all multiplied by the volume of the material. In plain English, it means that larger objects, made of more flexible materials, put under higher stress, essentially act like massive invisible batteries. They're just storing kinetic energy, waiting for that force to be released. Okay, section 4, application, riveted joints. This is where we seamlessly pivot from abstract equations into building the real world. When you're joining massive plates of metal together, say for a high-pressure boiler or a ship's hull, you basically have two fundamental options. Over on the left is the lap joint. It's exactly what it sounds like. One plate overlaps the other, and a rivet goes straight through both. It's simple, it's effective. But on the right, you've got the butt joint. Here, the two main plates are pushed end to end, so they're just touching, and then cover straps are placed over the seam before the whole thing is riveted together. The choice between overlapping them or buckling them end to end depends entirely on how the engineer wants to manage those physical shear stresses we've been talking about. And depending on the structural demands, engineers can scale up the complexity of these joints. You might just use a basic single riveted lap joint for a relatively light load. But if you're building a highly pressurized steam shell, you're going to need to upgrade to something like a double riveted lap joint, or maybe even the granddaddy of them all, the double riveted double strap butt joint. That's where multiple rows of rivets and thick cover plates work together to distribute those sliding forces over a massive area, keeping the shear stress safely out of the danger zone.
And finally, Section 5, Designing Against Failure. Welcome to the climax of our structural journey, where we try to outsmart destruction.
So, when a joint gets pulled apart by excessive force, it doesn't just fail randomly. It essentially has four distinct choices. 1. The metal plate itself can literally tear right across the line of rivet holes. 2. The rivet itself can be sheared, like physically sliced perfectly in half by the sliding plates. 3. The immense pressure can cause the rivet to just crush the metal plate it's resting against. Or 4. The edge of the plate can shear away entirely. And what's incredibly satisfying here is that every single one of these failure modes has a precise mathematical equation. This allows engineers to predict the exact load that will trigger a disaster, long before it ever happens. Actually, just looking at these diagrams really brings the math to life. In Diagram 1, you can see the jagged, chaotic line of the plate tearing right between the holes. In Diagram 2, notice how that top plate slides directly over the bottom plate, leaving half a chopped rivet behind. And Diagram 3 shows that awful oval-shaped distortion of a crushed hole. Seeing this really drives home the point that an engineer's job isn't just about making things strong. It's about anticipating the exact shape of destruction and then designing around it. So how do engineers actually measure true success here? Well, they calculate something called joint efficiency. And it's a pretty harsh reality check, to be honest. The efficiency of your joint is based strictly on whichever of those 4 failure points is the weakest link. You calculate the absolute least amount of load required to cause any of those failures, and you divide it by the load the solid uncut parent plate could have carried on its own. So if your rivet can hold 1,000,000 pounds, but the plate tears at just 1,000 pounds, well, your efficiency is terrible. Real engineering is agonizing over every single variable, the rivet diameter, the plate thickness, the pitch between holes, until the strength against tearing is perfectly, beautifully balanced with the strength against shearing and crushing. We've just walked through the precise physics of sliding forces, and we've seen how engineers use straps, rivets, and some pretty brilliant math to combat shear stress. But it kind of leaves you wondering, if every single joint is ultimately mathematically limited by its weakest link, are we ever truly building unbreakable structures? Or is the highest form of human engineering really just the exquisite art of managing and delaying inevitable failure? It definitely changes how you look at the bridges and buildings around you every single day. Keep questioning those invisible forces holding your world together, and we'll catch you in the next one.